Okay, for with respect to second model, I think I have covered all the problems. Only one problem is left. Okay, in future I will be covering that problem also. Okay, we'll start model 3. For your second internal, model 2 and model 3 will be there. Okay, in model 3, you read up to first 5 problems. Okay, that will be the syllabus for your second I. Okay, with this I will start the class. So model 3 is of designing the sections for Flexure. Not only designing the PSC sections, analysis is also there. Analysis means finding moment carrying capacity of the pre-stressed concrete beam. That will also be there. Okay, therefore the course outcome of this model is, after successful learning of this model, you will be able to analyze and design a pre-stressed concrete beam. That is the course outcome. Okay, now, so as I said, there are two parts in this model. One is analysis, one more part is design. Analysis is nothing but you need to find moment carrying capacity of the section or moment of resistance of the sections. Okay, the cross section of the beam and the area of the pre-stressing steel. Okay, all the design details will be given. Okay, for the given beam, you need to find what is the moment carrying capacity. You need to find what is the moment of resistance of that beam. Okay, for the given parameters. For the given parameters means sectional dimensions like width of the beam, depth of the beam will be given. Okay, the grade of the concrete will be given, grade of the steel. Okay, grade of the pre-stressing steel will be given, and area of the pre-stressing steel will be given. Using all these data, you need to find what is the moment carrying capacity, what is the moment of resistance of the beam, whether it may be rectangular beam or it may be flanged beam or T beam. Okay, this is one part. One more part is designing of the PSC beam. They will give some loading condition. For that loading, you need to find suitable pre-stress concrete beam, okay, which can handle the given loading conditions. Either it may be rectangular beam or it may be T beam. That is the one more part. Okay. Now we'll see how to find this moment of resistance of a beam, PSC beam. Okay. To find moment of resistance, as in case of reinforced concrete structures. Okay. As in case of RCC, you will use IS 456 to find the moment of resistance. No. Similarly, here we will use IS 1343 1980 code book for finding moment of resistance of a PSC beam. Okay, we will use this IS 1343 1980 code book for finding moment of resistance of a PSC beam. Okay, here the clear-cut guidelines and some useful formulae are given. Using this guideline and the formula, you need to find the moment of resistance. Okay. Now what I will do, I'll just explain how to find moment of resistance of a PSC beam. The finding of moment of resistance or analysis of this PSC beam almost similar to RCC beam only. Okay, the basic principle behind the analysis is same only, but there it is RCC beam. Here we will have PSC beam. Okay, we have to make necessary changes accordingly while analyzing a pre-stressed concrete beam. Okay, the basic principle remains the same only. Okay, like stress block parameters. Okay, or the grade of concrete we have to take into consideration. Grade of steel we have to take into consideration. Okay, area of the section, area of the pre-stressing steel. Okay, same parameters here we will be considering for analyzing a PSC beam, like in RCC beam. Okay. Now I'll explain the procedure of finding moment of resistance of a rectangular beam or a T beam. Okay, rectangular beam or a T beam. Okay, so to find this moment of resistance, a formula is given. A formula is given in IS 1343 code book in the page number 59. Okay, page number 59. Let me show that here. Here you can see that formula. Okay. Here you can see that formula. M is equal to FPU AP into D minus 0.42 XU. Okay. We will use this formula to find moment of resistance of a rectangular beam and moment of resistance of a T beam provided the depth of neutral axis lies within the flange. Okay. Depth of neutral axis lies within the flange. Here you can say the depth of neutral axis lies within the flange. Okay, we will utilize this formula for the rectangular beam and T beam with depth of neutral axis lies within the flange. If the depth of neutral axis lies beyond the flange or the depth of neutral axis lies within the web, then procedure is different. I will be explaining later. Okay, so we will utilize this formula. M is equal to FPU AP into D minus 0.42 XU, which is given in page number 59 of IS 1383 codebook, where FPU is ultimate tensile stress in the tendon or ultimate tensile stress in the pre-stressing steel. Okay, and AP ultimate tensile stress means what? The stress in the steel at the moment of failure. Okay, the stress in the pre-stressing steel at the moment of failure at ultimate moment. Okay, it's called as ultimate tensile stress. Okay, and AP is area of pre-stressing steel. AP is area of pre-stressing steel. T is effective depth. X is depth of neutral axis. Okay. And here we have some few more additional terms, that is FP. Okay. FP is nothing but characteristic strength of cable or characteristic strength of pre-stressing steel, like FI in RCC. Okay, FP is called as characteristic strength of cable and FPE is effective pre-stressing stress after all the losses. If there is loss of stresses in the PSC beam, after considering the loss of stresses, whatever the remaining stress, final stress, it is there, that is called as effective pre-stressing stress and it is denoted by FPE. Okay. And in this formula, we don't have the term FP, correct? So in this equation, we don't have the term FP, even we don't have the term FPE, correct? But these are required to find the value of FPU and XU. To find the value of ultimate tensile stress and depth of neutral axis, we need the value of FP. Okay, that is characteristic strength of the cable is required. Okay, now in the problem, they will be given with all these values. Okay, area pre-stressing steel will be given. Okay, and characteristic strength of the cable will be given and sectional dimensions, width and depth of the beam will be given. Using all this data, you need to find moment of resistance. Okay, now what we will do to find this FPU will not be directly given in the problem. Even the depth of neutral axis XU will not be given in the problem. You need to find them and substituting in this equation, you will get moment of resistance. Now the question is how to find this FPU, correct? How to find this FPU and XU? Let us see. There is a clear-cut guideline in the code book. To find FPU and XU, we will utilize this table 11 and table 12. Okay. Using table 11 in the table 12, we will find the value of FPU and XU. Okay. Now the question is which table particularly we have to use, table 11 or table 12, correct? So depending upon the beam, whether it is pre-tensioned or post-tensioned, we will use table 11 or table 12. Okay, remember for a pre-tensioned beam, for pre-tensioned beam, we will use table 11. Okay, we will use table 11. Okay, this table 11 only we will use for if it is a pre-tensioned beam. If it is a post-tensioned beam, post-tensioned beam with effective bond, with effective bond, then we have to use table 11 only. Okay, if it is a post tensioned beam with the effective bond, here you can see with effective bond, then we have to use this table 11 only. Effective bond means if in case of post tension beam, what happens? There will be ducts provided in the beam. In the ducts, there will be cables. Okay, there will be cables. Correct? There will be cable or pre-stressing steel. Okay. If this pre-stressing steel is covered by a cement mortar in the duct, okay, if the pre-stressing steel is covered by cement mortar, okay, if it is grouted, whatever the space which is left out in the duct, okay, duct, if it is filled with this cement mortar, then it is called as post tensioned beam with effective bond. There will be an effective bond between the pre-stressing steel and the surrounding mortar, surrounding grout which is employed into the duct. Okay. So in this case, we have to utilize this table 11 only. Okay. For example, if he says in the problem pre-tensioned beam, then you need to use this column. Okay. For finding, initially we have to use the area pre-stressing steel will be given as I said in the problem. FP is nothing but characteristic strength of the pre-stressing steel will be given. Width and depth of the beam will be given. Grade of concrete used will be given. Okay. So using all these data, you will find this ratio AP divided by BD Okay. This formula is there, no? This formula is similar to that of formula which is there in page number 96 of IS 456. Okay. That is AST, sorry, AST by BD and FI by FCK. Formula is there now in page number 96. It is similar to in place of AST we have AP divided by PD. In place of FI we have area characteristic strength of pre-stressing steel FP by FCK. Similar to that. Okay, we need to find this ratio. Okay. If you find the value of this this ratio, okay, with corresponding to that value, we will find the value of FPU by 0.87 FP. Okay, in the by referring the pre-tensioning column. Okay, FP will be known. Okay, then FPU you can get it. What we will do? First, we will find this ratio. After that, corresponding to this ratio, we will find corresponding FPU by 0.87 FP. Okay. Knowing the value of FPU by 0.87 FP, you can find the value of FPU because FP value is also known. FP value is also known. Okay, by this you will get FPU value. Similarly, using this another column of pre-tensioned beam or pre-tensioning, you will find the ratio of XU by D. Okay, you will get some value here by referring this column. If you substitute D value here, you will get the depth of neutral axis. Now you got depth of neutral axis. You also got the value of FPU, substituting both FPU and XU and AP will be given in the problem, and depth of the effective depth will also be given. Substituting all the things, you will get the moment of resistance. Very simple procedure. Okay, this is the procedure for pre-tensioned beam. Okay, in the same fashion, we have to follow the same procedure for post-tensioned beam with effective bond and without effective bond. Okay, in the problem it will be clearly said. Okay, post-tension beam with effective bond, post-tension beam without the effective bond, like that it will be clearly said. If he says post-tension beam with effective bond, we need to refer these two columns. Okay, and we have to find FPU by 0.87 FP, and referring this column, we will get XU by D value. Okay, then by these formula, you will get FPU and XU substituting, you will get the moment of resistance. Okay, in the problem, if it says post-tensioned beam without effective bond, if this whatever the space left out in the duct, if it is not filled with cement mortar, then it is post-tension beam without effective bond. or unbonded tendons. You can see here. Conditions at the ultimate limit state for post-tension rectangular beams having unbonded tendons. Unbonded tendons. Okay. So here also the ratio, we have to find this AP FP by BD FCK ratio. Okay. Knowing this ratio, you will get uh, knowing you have to find two things here. AP FP divided by BD FCK and L by D ratio we need to find corresponding to this AP FP by BD FCK and L by D ratio. You will get the value of APU by FP from this column. Okay. Similarly, knowing this ratio and corresponding to some L by D ratio, L by D ratio are provided here. You can see here. Okay. Corresponding to the L by D ratio, you will get XU by D. By this, you will get XU. Okay, so knowing XU and FP, if you substitute in this formula, you will get the moment of resistance. Okay. Now, whatever the procedure which I explained now, it is the procedure for rectangular beam, and T beam provided the depth of neutral axis lies within the flange. Depth of neutral axis lies within the flange. Okay. If the depth of neutral axis lies in the web, then what is the procedure? Correct? Huh? If the depth of neutral axis, here you can see students, case 1, neutral axis lies within the flange, same as rectangular beam equation. Whatever the procedure I explained, same procedure we have to utilize. Okay. If the neutral axis lies within the web, okay, if X is greater than DF, then we have to utilize the formula for moment of resistance which is given here. Okay, we have to utilize this formula. Okay, this formula is not given in the code book. You need to remember this formula. Okay, if the depth of neutral axis lies within the web, then you need to use this formula for finding the moment of resistance, not the one which is given in the code book. Okay. Now here we can go through the formula. What is the formula? APU into APW, FPU into APW into D minus 0.42 XU plus FP into APF into D minus DF divided by 2 is the formula which you have to use for finding the moment of resistance. Okay. See, when the depth of neutral axis lies in the web, no? When the depth of neutral axis lies in the web, then this area of pre-stressing steel is divided into web and flange portion. Okay, the total area of pre-stressing steel is divided into area of pre-stressing steel required for web, area of pre-stressing steel required for the flange portion. Okay, in the problem, AP will be given, corresponding APW, APF will not be given. Okay, but we have the formula for finding APF, means area of pre-stressing steel required for flange section. Okay, utilizing this formula, we will get the APF value. If you substitute APF value and AP value here in this equation, you will get the APW. You will get the APW value. Okay. Now, while finding this ratio, no, here AP by BD FCK, instead of taking AP by BD FCK, we will take APW by BWD into FCK. Okay, we will find this ratio. Corresponding to this ratio, we will find these values and we'll get to know about FPU and XU. Substituting this in this equation, you will get the moment of resistance. So this is how we find moment of resistance of a flanged section with the depth of neutral axis lies within the web. Okay, I hope you got some idea on finding this moment of resistance of a pre-stress concrete beam. If you have any doubts in this explanation, you can ask students. If you got any confusions while solving a real problem, definitely you will get clarified with the procedure. Okay, and in between I have written some theory. Okay, it is like stress block parameters. Okay, I hope you all studied stress block parameters in RCC. Similarly, here I have written stress block diagram for PSC beam. Okay, what happens here? So this is the stress block diagram for a beam with depth of neutral axis lies within the web. Okay. So initially some portion of the stress will be rectangular. It will be constant. After that, it will be parabolic in nature. Parabolic in nature. Okay, if you want to find a resultant compressive force in this member, this point for this rectangular and parabolic, there it is this whole figure is combination of rectangular and parabolic. No, for this we will find an equivalent rectangle having the constant width of 0.36 fck. Okay, so 0.36 fck means area of this rectangle is equal to area of this rectangle plus parabola, means we will find an equivalent width of stress block. Equivalent width will be giving the same area. So equivalent width will be 0.36 fck. Okay, 0.36 fck into BW. Into BW means width of the web into XU will give compressive force in the section. Similarly, tensile force will be determined using multiplying stress in the ultimate stress in the steel multiplied by area of pre-stressing steel in the web will give tensile stress. This and this compressive stress C2 will be equal to tensile stress to maintain the equilibrium. Similarly, here I written the stress block diagram for the beam with depth of neutral axis lies within the flange. If the depth of neutral axis lies within the flange, it will be a constant stress distribution. Constant stress distribution. Okay. So 0.45 FCK into BF minus BW. BF minus BW means so this is BW, this is BF width of flange. Okay. So area of this portion. Area of this portion. BF minus BW will give area of this portion into DF, area of the shaded portion. 0.45 FCK is the stress and BF minus BW is the area. Stress multiplied by area will compressive area. Stress multiplied by area will give compressive force. Similarly here stress multiplied by area of web portion BW into XU will give area multiplied by compressive stress. See, when the depth of neutral axis lies within the web, we will consider width of the web and depth of neutral axis. When the depth of neutral axis lies within the flange, we will find the area corresponding to flange leaving the this web portion. Okay, and multiplying by depth of flange will give area multiplied by 0.45 FCK is the stress distribution. Stress multiplied by area will give compressive force and tensile force will be same. To maintain the equilibrium, this T tensile force will be equal to compressive force. Okay. So I hope you got some idea on analysis of PSC beam. Now we will move on to solving the problem. Just write this problem, students. Yes. All of you read this problem. Problem number 1. Take 1 minute time to write the problem. Okay. So these are all very simple problems. You can easily solve these problems on model 3. You just go through it. A pre-stressed concrete beam of rectangular cross section 200 by 500. Let me write the cross section of the beam. Solution He says it's a rectangular cross section. Rectangular cross section having 200 width and 500 depth. Okay. B is equal to 200 mm and overall depth is given as 500 mm. 500 mm. Okay. Here you can write B is equal to 200 mm and D is equal to 500 mm. Okay. Deep is pre-stressed by tendons having an area of 600 mm square. Area of pre-stressing steel is given. Okay. AP. AP is equal to area of pre-stressing steel. Area of pre-stressing steel AP is given. It is given as 600 mm square. It is given as 600 mm square. Located 100 mm from socket of the beam. Okay, this area of pre-stressing steel now. It is located at a distance of 100 mm from socket of the beam. Okay, means the effective depth D becomes how much? Effective depth, therefore, effective depth D will be equal to overall depth is 500 minus effective cover is 100 mm. So effective depth will be 400 mm. Okay. Then what else is given? Given FCK is equal to 40 Newton per mm square. Grade of concrete is given. FCK is equal to 40 Newton per mm square. Then FP, grade of steel, grade of pre-stressing steel. FP is given as 1600 Newton per mm square. This is sometimes this value will not be given, students, in the problem. Sometimes, okay. If it is not given, this is the standard value. You need to remember this number and you need to utilize the same value for doing the calculation. Okay. If the FP value is not given, you need to assume it has 1600 Newton per mm square. Grade of steel, estimate the ultimate flexure strength of the beam. Okay. We need to estimate moment of resistance. Okay. As per the IS code recommendation, when the beam is pre-tensioned, and we need to estimate the moment of resistance when the beam is post-tensioned with the effective bond. Okay, first we'll solve the first question. Okay, if the beam is pre-tensioned, first one. First question. If the beam is pre-tensioned, the beam is pre-tensioned. Okay, it is a rectangular beam. For rectangular beam, we know the formula to find the moment of resistance. Okay, here we have the formula. So copy this formula here. We know that ultimate flexural strength is given by MR is equal to, what is the formula there? FPU into AP D minus 0.42 XU. FPU into AP into D minus 0.42 XU. Okay. This is available in IS 1343 1980 page number 59. Page number 59. Okay. Now we have to find the value of FPU, AP, D is known, effective depth is known. Area pre-stressing steel is also given. How much it is given? 600 mm square. We need the value of FPU and XU. To find this value of these FPU and XU, we have to utilize table 11. Okay, using this table 11. Okay, the type of beam given is what? Pre-tensioned beam. You need to refer this column. Let me erase all the things. Okay, we need to utilize this pre-tensioned column. Okay, for finding FPU by 0.87 FP and XU by D. Okay, initially what we need this value AP divided by BD FCK value we needed. First you find that. Okay, from table below, right? From table 11, page number 59 of IS 1343, IS 1343 1980. The ratio, what is that ratio? AP FP divided by BD FCK. AP FP by BD FCK is equal to area pre-stressing steel is given as 600 and FP value is given as 1600. Characteristic strength of the pre-stressing steel divided by width of the beam is given as how much it is given? 200 and effective depth is 400, not the overall depth. 200 by 400 and grade of concrete is given as 40. Okay, so what is the answer that you get for this? Please check the answer. It is 0.3. Okay, answer which you get is 0.3. Okay, now we got the ratio AP divided by BD FCK, that is 0.3. Okay, so corresponding to 0.3 of AP FP by BD FCK value, you need to find the value of FPU by 0.87 FP using this pre-tensioning column. Okay, so we got 0.3 as this ratio. 0.3 where we have, just find it. 0.3 here we have that value. Okay, corresponding to this 0.3 and corresponding to pre-tensioned beam. Okay, the value of FPU by 0.87 FP is 1.0. Below you write from table 11 for AP FP by BDFCK is equal to 0.3. The corresponding this FPU by 0.87 FP. FPU divided by 0.87 FP is how much? 1. Is 1.0. Okay, so that is pre-tensioning column we need to refer. Okay, now FP value is known. Characteristic strength of the steel, that is 1600. Just substitute FPU divided by 0.87 into 1600 is equal to 1.0. By this you will get the value of FPU. Ultimate tensile stress in the steel, you will get it. Okay, if you calculate the answer, you will get the answer as 3392 Newton per mm square. Okay, 1392 Newton per mm square. Okay, similarly corresponding to APU, AP divided by BD FCK value of 0.3, we need to find XU by D value by referring this pre-tensioning column. Corresponding XU by D value with respect to 0.3 is how much? It is 0.655. 0.655. Okay, below, right? And for AP FP divided by BD FCK is equal to 0.3 corresponding XU by D is equal to 0.655. 0.655. Okay. So just substitute the effective depth value here. XU by 400 is equal to 0.655. Therefore, XU is equal to, if you multiply 400 and 0.655, you'll get the answer as 262 mm depth of neutral axis. Okay. Now you got the value of depth of neutral axis. You got the value of ultimate tensile stress in the pre-stressing state. Substitute in this equation. Okay. Call this as equation number 1. Therefore, the equation 1 becomes. Therefore, the equation 1 becomes MR is equal to FPU value is 1392 into AP is area of pre-stressing steel. How much it is given? 600 mm square into 600 into D minus 0.42 x. D is effective depth is 400 minus 0.42 into XU is 262 mm. By this we will get moment of resistance or MU. We will get the answer as 242.17 into 10 power 6 Newton millimeter, or MR is equal to 242.17 kilonewton meter. This completes the first problem. Okay. Any doubts in this problem you can ask in this step. Okay. Now we have solved first question. Now we will solve second question. If the beam is post tensioned with effective bond, the beam is second question. Second question. If the beam is post tensioned with effective bond, what is the moment of resistance? Is the question. Okay. Post tensioned with effective bond is here. Instead of referring this pre-tensioning column, you need to refer this column. Post tensioning with effect. These values will change. Means FPU by 0.87, FI 0.87 FP becomes 0.85, and 60 by D will become 0.558. That's it. Okay. That is only the change. Okay. So formula is same only. MU is equal to FPU AP into D minus 0.42 XU is the formula. So from table 11, page number 59, for APFP by BDFCK is equal to, it is same only 0.3 only. We already calculated this ratio 0.3. Corresponding FPU by 0.87 FP is equal to how much it is? 0.85, and XU by D is equal to 0.558. Okay. Just substitute the value of FP here. Therefore, FPU divided by 0.87 into 1600 is equal to 0.85. By this, you will get the modified FPU now corresponding to post tension case. FPU will get it as 1183.2 Newton per mm square, and If you substitute the value of effective depth, that is 400 mm here, 0.558, you will get the modified depth of neutral axis corresponding to post incident case, 223.2 millimeter. 2 millimeter is the answer. Similarly, substitute in this equation. Therefore, mu is equal to mu or mr, whatever. Mu is equal to FPU is 1183.2 into AP is 600 into D minus 0.42 XU, 400 minus 0.42 into 223.2 millimeter. By this, you will get the ultimate moment of resistance as 217.41 into 10 power 6 Newton millimeter, or mu is equal to 217.41 kilonewton meter. This completes the problem. Very simple problems. Any doubts you can ask? Thank you. Now we'll move on to the next problem. Please write the second problem. Okay, this is the problem on T section. It is a problem on T section. Go through it. A pre-tensioned T section having flange width of 1200 mm and thickness of flange is 150 mm, width and depth of rib is 300 and 1500 mm respectively. Let me write the diagram of a T section. Okay, flange width is 1200 mm. Width of flange is equal to 1200 mm. And thickness of flange is 150 mm. Thickness of flange or depth of flange DF is equal to 300 mm. 300 mm. Sorry, 150 mm. Okay. Width and depth of the rib is given. Width of the rib is width of web is equal to 300 mm. And depth of web is also given. DW is equal to it is given as 1500 mm. Okay, the area of tensile steel is 4700 mm square located at an effective depth of 1600 mm. This is EP. Okay, and he says that this area of steel is located at an effective depth D is equal to 1000. How much it is? 1600 mm. 1600 mm. Okay, if the characteristic cube strength of the concrete and steel is 40 and 1600 Newton per mm square, calculate the flexure strength at limit state of collapse in flexure for the T section as per the IS code provisions. Okay. Now, Once again, I'll write all the data here as given parameter. BW is equal to 300 mm. Depth of web is equal to 1500 mm. And effective depth is equal to 1600 mm. Okay, area of pre-stressing steel 4700 mm square. 4700 mm square. Then FCK, characteristic strength of concrete, is given as 40 Newton per mm square. 40 Newton per mm square. And characteristic strength of pre-stressing steel is given as 1600 Newton per mm square. Correct? We have to find mu, ultimate moment of resistance. Okay. Now for T section, we have to first identify whether the depth of neutral axis lies within the flange or the depth of neutral axis lies within the web. That we don't know. Correct? We don't know whether the depth of neutral axis lies within the flange or whether it lies in the web. Okay. For that, what we have to do is we have to assume some particular case. We have to assume some particular case. So what we will do? We will assume that the depth of neutral axis lies within the flange only. Okay. Now step 1 you write. Step 1. Step 1. Assume neutral axis lies within the flange. Okay. Means depth of neutral axis lies within the flange. Okay. Assuming that depth of neutral axis lies within the flange, we will find XU by D value. Okay. See, there are the procedure different. The procedure of finding moment of ultimate moment is different if the depth of neutral axis lies within the flange, and the procedure is different if the depth of neutral axis lies within the web. First, we have to identify whether the depth of neutral axis lies within the flange or web. Okay. For that purpose, what I have done is I have assumed that neutral axis lies within the flange. Okay. If the neutral axis lies within the flange, whatever the procedure we follow for rectangular section, okay, whatever the procedure we followed for rectangular section in the previous problem, same procedure we have to follow. Okay, and it is a pre-tensioned beam. It is a pre-tensioned beam. Okay. Now what we'll do is okay. Now what we'll do is now what we have done is we have assumed that the depth of neutral axis lies within the flange. If the depth of neutral axis lies within the flange, the procedure is similar to that of rectangular section. Okay. Now what we'll do, we'll find this ratio. Okay. We'll find this ratio. Corresponding to this ratio, we will find XU by D. Okay. If you get to know about XU by D, if you substitute the effective depth, you will get the value of XU, that is depth of neutral axis. Whatever the value you get it, this depth of neutral axis, if it is less than DF, then our assumption is correct. If it is greater than DF, then our assumption is wrong, means that the depth of neutral axis lies within the web. Okay. This is how we check whether the depth of neutral axis lies within the flange or within the web. Okay, now what I have assumed is, I have assumed that depth of neutral axis lies within the web. Sorry, within the flange. Okay, now you find this ratio AP by BD FCK. Below, right, from table 11, AP, FP divided by PD, FCK is equal to AP, FP divided by, here B is there. B, here you will have confusion whether to substitute width of flange or whether to substitute width of web. Okay, that is the confusion you will be having. See, what you have done is, you have assumed that depth of neutral axis lies within the flange. Okay, as you assumed depth of neutral axis lies within the flange, here you need to substitute width of flange only. Width of flange only. PF into D into FCK. This is very important. Remember this, students. Remember this. Okay, you assumed depth of neutral axis lies within the flange, so you need to substitute width corresponding width of flange only here. Therefore, AP, FP divided by PD, FCK. AP is given, FP, everything is given, just substitute. 4700 into FP is 1600. 4700 into 1600 divided by width of flange is 1200. 1200 into effective depth is 1600. 1600 into FCK 40. If you estimate this value, you will get the answer as 0.098. Okay. Now you got the value of this ratio, that is 0.098, corresponding to 0.098. You need to estimate the value of XU by D. And what is the type of beam given? It is pre-tensioned beam given in the problem. Okay, in the problem he said that it is a pre-tensioned beam. Okay, now you need to refer this column. You need to refer this column. Okay, to find the value of XU by D. Okay, corresponding to APFP by BD FCK value of 0.098. 0.098. So here we have the value for 0.098, means here we have the value for 0.05. We have the value for 0.10. So by interpolation, we have to find the value for 0.098. For 0.05, we have the value of XU by D as 0.109. For 0.10, we have the value of XU by D as 0.217. Let me write here the same thing from table 11. From table 11, for APFP by PF into D into FCK is equal to 0.05. The corresponding XU by D is 0.109. 0.109. You need to refer pre-tensioning column. Okay. Similarly, for 0.10, corresponding XU by D is equal to 0.217. 0.217. Then we need the value for 0.098. Okay. Now you need to do the interpolation, friends. You are very much familiar with doing the interpolation. Just do the interpolation and get the value for 0.098. Okay. Therefore, after interpolation, for AP FP by DF into D into FCK is equal to 0.098. You will get the corresponding XU by D after interpolation as 0.213. We will get the value as 0.213. Now, substitute the value of effective depth now. XU by effective depth is given as 1600 is equal to 0.213. Okay. Therefore, XU, depth of neutral axis, if you multiply by 1600 and 0.213, you will get the answer as 340.89 millimeter. Okay, just look into the figure. Depth of, which means depth of neutral axis is 340.8 mm. 340.8 mm is, it is going beyond the flange. Depth of flange is only 150 mm, but depth of neutral axis we got is 340.8 mm, which means that our assumption is wrong. Depth of neutral axis lies within the web, not in the flange. Correct? So this value is greater than depth of flange. Therefore, our assumption is wrong. Hence, assumption is wrong. Okay. Therefore, now the neutral axis lies within the web. Okay, neutral axis lies within the web. Okay. This is step 1, students. What is step 1? To find the location of the neutral axis, whether it is lies in the web or the flange. For that, what I have done is initially I assumed one particular case, that is neutral axis lies within the flange. I have done corresponding calculations. Finally, I got depth of neutral axis as 340.8 mm, which is greater than depth of flange, which means that the neutral axis not lies in the flange, it is lying in the web portion. Okay, now we came to know that neutral axis lies within the web. Okay, if the neutral axis lies within the web, then procedure for finding the moment of resistance is different. Case 2, it will come under case 2, neutral axis lies in the web. We need to utilize this formula. This formula is not given in the code book. You need to remember this formula, students. We need to remember this formula. Okay? Below, right? That formula. If step 3, right? Sorry, step 2. Step 2. Now, you need to utilize this formula to find the moment of resistance. In this formula, you can see that APW is there. Okay, APW means area pressure steel in the web portion, FPO. Okay, ultimate tensile stress is there. APF is there, area pressure steel required for flange portion. Okay, then you need all these values, correct? These values we need. First, you find now in the step 2, what you do is you find area of pre-existing steel required for web portion and the flange portion. How will find it? Utilizing this formula. APF is equal to 0.45 FCK into BF minus BW into DF by AP. Using this formula, you will get the area of pre-existing steel required for the flange portion. Knowing the total area of steel and knowing the area of pre-existing steel required for the flange portion, you can easily find APW. Okay. Now in the step 2, area of pre-stressing steel required for flange and web portion. Means we need the value of APF and APW. That we'll find now in this step. So we know the formula for finding APW, APF 0.45 FCK, BF minus BW into DF by FP. We know that APF is equal to 0.45 FCK into BF minus BW into DF by FP. Okay. Therefore, APF is equal to 0.45. FCK is 40 Newton per mm square, which is given in the problem, into width of flange. How much we have? Width of flange is 1200 and width of web is 300. 1200 minus 300 into depth of flange we have as 150 mm and characteristic strength of the precision steel is 1600. By this, we'll get the area of precision steel required for the flange portion. You please check the answer. It is 1518.75 mm square APA. Okay. Now, the total area of steel will be equal to area of pre-stressing steel in the flange portion, area of pre-stressing steel in the web portion. Total area of steel AP is given in the problem. How much is given? 4700 mm square. 4700 is equal to APF is 1518.75 plus APW. By this we'll get the value of APW, that is 3181.25 mm square. Okay, why we are calculating APF and APW? Because they are needed for calculating moment of resistance here. Okay, now in the step 3 we can go for calculating this moment of resistance. We know that copy that formula as it is. We know that formula is mu is equal to FPU into APW into D minus 0.42 XU plus FP into APF into D minus DF by 2. D minus DF divided by 2. So the same formula I copied here. Okay. Now APW is known, APF is known, effective depth is known, depth of flange is known. Okay, effective depth is known. Only the thing is we need to calculate the value of FPU, ultimate tensile stress. Okay, and depth of neutral axis. Correct. FP value is also known. It is 1600. Okay, we need the value of FPU and XU. Okay, to calculate the value of FPU and XU, we have to refer the table of the IS 1343 code book. Okay, so in the problem he clearly says that it is a pre-tensioned beam. Pre-tensioned beam. So we need to refer this pre-tensioning case. We need to refer the pre-tensioning case for finding this ratios FPU by 0.87 FP and XU by D. Okay. Now, first you find this ratio AP by BD FCK. So here you write the sided line as to find, or else directly find that ratio from table 11. From table 11, what is the ratio we have? It is AP by BD FCK. AP by BD FCK. AP by BD FCK. Now we have to rewrite this formula corresponding to the depth of neutral axis lies within the web. Okay. So corresponding to depth of neutral axis lies within the web, the formula can be rewritten as APW into FP divided by PW into DFCK. Okay. I have made two changes here. AP I have changed to APW and B I have changed to width of web. Okay. So in the first case, we need to substitute the full area of resistance only, AP only. Okay. Only one change in the first case, that is width. Here, in the second case, you have to change A as APW and B as BW. Remember, students, this step is important. Okay. Now, substitute all corresponding values. Okay. All corresponding values is equal to APW. Just now we have determined it is 3181.25. 3181.25 into FP. We know already it is 1600. 1600 divided by PW width of web is 300 mm into FAT depth is 1600 mm. FCK is 40. If we calculate the ratio, we will get the ratio as 0.265. Okay. Now corresponding to the value of 0.265, we need to find the value of FPU by 0.87 FP and XU by D. Okay, referring this pre-tensioning columns. Okay. So what is the ratio we have? 0.265. 0.265 means it will fall between 0.25 and 0.3. Okay. See, for 0.25 corresponding FPU by 0.87 FP is 1 and for 0.3 also 1. Therefore, corresponding to 0.265 the value will be 1 only. It will be 1 only. Okay. Below you write from table 11. From table 11. From table 11 for APW into FP by BW into D into FCK is equal to 0.265. Corresponding FPU by 0.87 FP is 1 only. FPU divided by 0.87 FP is equal to 1.0. Okay, pre-tensioning column. 1.0. Okay. Now FPU divided by 0.87 FP value is given 1600 is equal to 1.0. Therefore, FPU will get it as 1392 Newton per mm square. Okay, similarly, you find the value of XU by D value. XU by D value corresponding to pre-tensioning column. For 0.25, we have the value of 0.542. For 0.3, we have the value as 0.655. By interpolation, you have to get the value for 0.265. Okay. Now, from table 11, from same table 11, from table 11, for APW into FP divided by PW into D into FCK is equal to 0.25. Corresponding XC by D value is 0.542. When that value is 0.30, corresponding value is 0.655. 0.655. We have to get the value for 0.265. Correct? We have to get the value for 0.265 after interpolation. After interpolation, this is XU by D values. Okay. XU by D values. Okay. So after interpolation, for APW FP by BW into D into FCK is equal to 0.265 corresponding XU by D. After interpolation, you will get the value as 0.576. 0.576. So XU by D, if we substitute, it is 1600 is equal to 0.576. Therefore, XU will get it as 921.6 mm. Okay. Now you can see that 921 means it is more than the depth of flange, means neutral axis lies in the web only. Okay. In web, neutral axis lies in the web. Okay. Now you got the value of XU, you got the value of FPU. Substitute in this equation. Okay. We call this equation as equation number 1. Therefore, equation 1 becomes, therefore, equation 1 becomes, if we just substitute all the values, we will get the ultimate moment of resistance. Okay. Mu is equal to FPU into APW. FPU value is 1392. 1392 into APW value is how much we have? APW 3181.25. 3181.25 into D minus 0.42x. You know, D is effective depth is 1600. 1600 minus 0.42 XU is 921.6. D minus 0.42 XU plus FP into APF plus FP. Characteristic strength of precision steel is 1600 into APF. Just before we have calculated how much we got is 1518.75. 1518.75. Okay. FP into APF D minus DF by 2 into 1600. Depth of flange is 150 by 2. Okay. So if you calculate the answer, you will get the value of ultimate moment of resistance as 9.076 into 10 power 6 Newton millimeter. Okay. Sorry, into 10 power 9. Okay. You can rewrite this value as 9.076 or 90,000. So 9,076. 9,076 into 10 power 6 Newton millimeter. In terms of kilonewton meter, it is Mu is equal to 9,076 kilonewton meter. Okay. This completes the problem. Okay. I hope you all understood. Still, if you have got any doubts at any point of calculation, you can ask. Okay. Now we move on to the next problem. All of you note this problem. So it is a problem on symmetrical double T section. Okay, there are two webs. Double T section is there are two webs. Let me read the diagram. What he says is a symmetrical double T section has a flange width of 1200 mm total, means total length, and 140 mm thick. First, let me read the diagram of a double T section. Okay. As flange width of 1200 mm. Total flange width is 1200 mm. 1200 mm. Okay. And 140 mm thick. Depth of flange is 140 mm. 140 mm. Overall depth of the beam is 1700 mm. Overall depth of the beam is given capital D. It is given as 1700 mm. 1700 mm. Then, and thickness of each rib is 150 mm. Here, 150. Think about BW. Okay, thickness of each rib is 150 mm. The member is stressed with an effective pressure force of 7,500 kilonewton through the cables located at a distance of 150 mm from soffit. Cables are located at 150 mm from soffit. 150 mm from soffit means you can calculate the effective depth, correct? Overall depth is given 1700, you can calculate the effective depth. And characteristic strength of the concrete is given, and characteristic strength of the steel is not given. If it is not given, we need to assume. Assuming that grouting is 100% effective, determine the ultimate moment of resistance. I will tell you what is the meaning of grouting 100% effective. First, let me list all the given data. Flange width 1200 mm. Then thickness of flange 140 mm. Then overall depth capital D 1100 mm, 1700 mm. 1700 mm. Then thickness of rib BW. BW is equal to 150 mm each. There are two Fs. Okay, there are two Fs. So 150 mm each. So while doing the calculation, you need to substitute the total width of the web portion. Okay, total width of the web portion is 150 plus 150, nothing but 300 mm. You need to substitute BW width of web. Okay, remember students, there are two web. Okay, both the webs will contribute towards handling the flexural stresses. Then the width of the web will be 300 mm. Okay. Then what else is given? The member is pre-stressed with a effective pre-stressing force P is given. P is equal to 7,500 kilonewton. Then through the cables located at a distance of 150 mm from the soffit, you can calculate the effective depth now. Overall depth is 1700 mm minus effective depth is given as 150 mm. Cables are located at a distance of 150 from soffit. So the effective depth becomes 1000 150, sorry, 1550, correct? 1550 mm. Okay. Then assuming that the grouting is 100% effective, estimate the moment of resistance. Characteristic strength of concrete FCK is 400, sorry, 40 Newton per mm square. FP is not given. We need to assume it as 1600 Newton per mm square. If it is not given, it is a standard value. Okay. Now, the pre-stressing force is given. P is equal to 7500 kilonewton. And area of cable is also given, I think. Area of each cable. Let me go through the problem. A symmetric T section has a flange width of 1200 and 140 mm thick. Overall depth is 1700 mm. Thickness of rib is 150. The member is pre-stressed with the effective pre-stressing force of 7500 kN through cables located at a distance of 150 mm from soffit. Characteristic strength of concrete is 40 Newton per mm square. Assuming the routing as 100% effective for ultimate find the ultimate resistance. Now, for calculation, we need the value of AP, correct? Huh? Area pre-stressing steel we need. Okay. Area pre-stressing is steel is required. We know the stress in the steel. Okay, stress in the steel, how much we have assumed? 1600 Newton per mm square. Force, pre-stressing force in the steel is known. Utilizing these two data, we can find the CAP area pre-stressing steel. Okay, we know that stress is equal to force by area, as we are finding with respect to cable, here area of cable, force in the cable divided by area of cable. Okay, the characteristic tensile stress in the steel, how much we assumed? We assume it as 1600. We have assumed it as 1600. Just a minute, students. Okay, we'll continue. So stress we assume it as 1600. Force that only that force in the cable it is given. It is given as 7500 kilonewton. 7500 kilonewton is nothing but into 10 power 3 Newton divided by area of cable AP. Okay, by this you can estimate the area of cable. If you estimate, you will get the answer as 4000 4687.5 mm square. Okay, 4687.5 mm square. Okay, by this you will get the value of AP. This AP is required for estimating moment of resistance. Correct? Huh? Now, so this is also T section. We don't know which is the case, whether the depth of neutral axis lies within the flange or depth of neutral axis lies within the web. We don't know. Okay, for that we need to make some assumption. Okay, in the previous problem, what I have done, I have assumed that the depth of neutral axis lies within the flange. Okay, I have assumed that depth of neutral axis lies within the flange, and I have estimated the XU by D value. By knowing the XU by D, XC if I calculate, I got 340, which is greater than depth of flange. Means assumption was wrong. Then I have gone for the second case, assuming the depth of neutral axis lies within the flange. I have estimated the moment of resistance. So in this problem, what I will do is, I will directly assume second case. Okay, I'll directly assume second case. Okay, if you want, you can assume first case, that is depth of neutral axis lies within the flange. Then you can estimate the neutral axis and you can compare the XU value with DF. Definitely you will get the XU greater than DF. Okay. Now what I will do is I will directly assume the depth of neutral axis lies within the web. Okay. You can, if you want, you can perform this first step. Okay, if you want, you can perform this first step. Okay, here I already know that depth of neutral axis lies within the web. I will assume directly the second case. Okay, in the examination, better to follow from first step only. Assuming depth of neutral axis lies within the flange, you perform the calculations, then you check whether assumption is correct or not. Then you proceed for finding the moment of resistance. Okay. Now, assuming step 1, I will directly assume neutral axis lies within the web. Okay, that is XU is greater than DF. I will directly assume second case. Okay, you can assume any case. If it holds good, you perform the moment of resistance. Otherwise, you go for the another case. That is the thing which we have to follow here. Then area of cable. First, if you assume the second case, we need APF and APW, no? Like we have determined here, we have to find this APF and APW. Okay, APF and APW we have to find out. Okay. Now, area of cable, AP is equal to sum of APF plus APW. But we know the formula for APF, but APF is equal to, we have the formula here, 0.45 FCK BF minus BW into FP by DF by FP. I will write the same formula, 0.45 FCK into BF minus BW into DF by FP. Okay, so everything is known. Just substitute. APF is equal to 0.45 FCK is given as 40. Width of flange is 1200 mm. 1200 mm minus width of web. Okay, it is 300 mm, not 150 mm. There are two web portions. Okay, so minus here, minus 150 into 2. 150 into 2. Okay, 150 into 2. Because 2 number of web. Okay, that is why 150 into 2. Okay, into df by fp, depth of flange, how much it is? Depth of flange is 140 divided by fp is 1600. That we have assumed 140 by 1600. If we estimate this value, we will get the answer as 1417.5 mm square. Okay. Now you can estimate the value of APW. We know that AP is equal to sum of APF, sum area pre-stressing steel in flange portion, area pre-stressing steel in web portion. AP, total AP is known. It is 4687.5. 4687.5 is equal to APF is 1417.5. 1417.5 plus APW. By this, you'll get the value of APW. How much is 3270 mm square? Please check the answer. 3270 mm square. Okay. Now we assume the second case. For second case, we have to estimate the ratio using the table provided in IS 1343 1980 code book. Concentrate here. Assuming that the grouting is 100% effective. Assuming that grouting is 100% effective means the grouting is done in the duct. Grouting is done in the duct means it is with the effective bond. Okay, indirectly he has given here. Okay, grouting is done is nothing but it is with effective bond only. Means you need to refer table 11 only. You need to refer table 11 only with effective. Instead of saying with effective bond, he said that grouting is done. Grouting is done is nothing but there is an effective bond between the area of pre-stressing steel and the surface of the duct. There is a filling of water. There is an effective bond. Okay, you need to refer this table 11 only. Okay, so according to this table 11, we need this ratio, that is APFP or BDFCK ratio we need, that we'll find now first. Okay, that we'll find now. Now from table 11, from table 11 of IS 1343, page number 59. The ratio required is APFP by BDFCK. APFP by BDFCK. You have to rewrite as per the second case. Okay, you have assumed depth of total axis lies within the web, then it becomes APW FP divided by BW to D into FCK. Okay, therefore APW is 3270 into FP. We have assumed it as 1600 divided by width of web is 300 is 2 into 150. 300 into 1550 is the effective depth into FCK is 40. If we estimate this ratio, we will get the answer as 0.28. 0.28. Now corresponding to the value of 0.28 and referring just look into it, it is a post tensioned beam. Okay, where we will do the grouting? Post tensioned beam only they will do the grouting. Is it mentioned clearly or not? Just check it. So when he says grouting is done obviously it is understood that it is a post-tensioned beam only. It is a post-tensioned beam only. Means we have to refer this column. Okay, for calculation of FPU by 0.87 FP, for calculation of XU by D, we need to refer this column. Okay, means post-tensioned case we need to refer. Okay, now we have already obtained this ratio. We got it as how much we got? We got it as 0.28. 0.28 means we have the value for 0.25. Okay, that is 0.9, and we have the value for 0.3, 0.85. By interpolation, we can get the value for 0.28. Okay. Now from table 11, okay, first you check whether the depth of neutral axis lies within the web or not. For that, instead of estimating this first ratio, you estimate this second ratio. Okay, because we will check whether depth of neutral axis lies within the web or not. We assume no. First you find XU by D. So corresponding to 0.25 and post-tensioned case, the value here is 0.488 and for 0.3 we have the value of 0.558. Let me copy the same value from table 11. From table 11, okay. From table 11 for APWFP by BW into D into FCK is equal to 0.25, corresponding XU by D is equal to how much we have? Here we have 0.488 for 0.25, 0.488, 0.488, and for 0.30 corresponding XU by D we have as 0.558, 0.558, but we need the value of for 0.28. XU by D is equal to question mark. Now by interpolation you can get this value. After interpolation, you will get the value of XU by D as 0.53. Okay, therefore XU by D is effective depth that we have as 1550 is equal to 0.53. Okay, then XU will be equal to 821.5 millimeter. Depth of neutral axis is at a distance of 821.5 millimeter, which is greater than depth of flange. Depth of flange is how much? Depth of flange is only 140 mm. Okay, so depth of neutral axis more than depth of flange means the neutral axis lies within the web portion. Hence, our assumption is correct. Okay, hence our assumption is correct. Hence, the assumption is correct. Okay. Suppose if in the case this XU comes less than DF, then it will fall under case 1. It will fall under case 1. Okay. Means using the guidelines of case 1. Okay. Using the guidelines of case 1, you need to find the moment of resistance. Okay. This as like a rectangular section, you need to estimate the moment of resistance. If this XU comes less than DF, now we are getting as per our assumption, getting the value as per our assumption, that is depth of neutral axis lies within the web, that is X is greater than DF, assumption is correct. Okay. Now XU we got, we need one more value FPU, refer this table. Okay, corresponding to 0.25, value 0.9, corresponding to 0.3, value 0.85, for 0.28 you can estimate. Okay. Now from table 11, from table 11 for APW divided by FP into FP divided by BWD FCK is equal to 0.25 corresponding FPU by 0.87 FP. FPU divided by 0.87 FP is equal to how much we have? We have 0.90. 0.90. When it is 0.30 corresponding FPU divided by 0.87 FP is 0.85. 0.85. But we want the value for 0.28. 28 corresponding FPU by 0.87 FP is equal to question mark. Here also we need to do the interpolation. Therefore, after interpolation of interpolation, we get the value corresponding to 0.28 as FPU by 0.87 FP as 0.87 only. Okay. Therefore, FPU divided by 0.87 FP we have assumed it as 1600 is equal to 0.87. By this we'll get the value of FPU, that is 1211 Newton per mm square. 1211 Newton per mm square. Okay. Finally, you got the value of FPU and XU. You can estimate the moment of resistance using the second case formula. What is the formula? This formula. Okay, let me write the formula. Last step, step 3. Step 3. Step 3. We know that if the neutral axis lies within the web, the formula for mu is equal to FPU into APW, FPU into APW into D minus 0.42 XU plus FP into APF D minus DF by 2 plus FP into APF into D minus DF by 2. Okay. Now each and every values are known. Just substitute and get the answer. FPU is 1211 into APW. How much we got? APW 3270 into 3270 into D. Effective depth is 1550 minus 0.42 into XU. XU is 821.5. 821.5 plus FP. FP value is 1600 as we know. 1600 into APF is how much we got APF value? 1417.5. 1417.5 into D 1550 minus DF by 2. Depth of flange, how much we have? The 140 divided by 2 minus 140 divided by 2. So all of you please calculate the answer and cross check the answer. The answer is 8.128 into 10 power 9 Newton millimeter, or mu is equal to 8128 kilonewton meter. Okay, it becomes 8128 into 10 power 6 means 8128 kilonewton meter. Okay, this completes the problem. If you got any doubts at any step, you can ask students.
Sir, notes.
Yes.
Sir, notes, sir.
Notes I will be sharing. Okay, immediately after this class, I will be sharing the notes and I will share you the link. You can download through that link. Any doubts here, students? Okay, thank you. I will end this class and I'll continue in the next class.